Yeah, thank you so much for the introduction, and thank you all for having me. I'm blessed to be one of the many companies here looking at epigenetics, and hopefully with one of the algorithms that we'll talk about today, we'll speak to that sort of, I think, what is a sort of a false dichotomy between health span and lifespan. So anxious to follow that discussion. Just to give a little bit of background on sort of who we are, we're a relatively new company. We sort of started doing commercial epigenetic testing, offering in July of 2020. However, in that time, we've had really one of the largest private databases for epigenetic methylation information that's been created. Since July of last year, we've done over 13,000 patients tested on really broad scale methylation related diagnostics. We've done that in our own facility. We have a 20,000 square foot CLIA certified lab in every state where we do some new custom arrays to reduce the cost and to sort of increase the coverage of some of these epigenetic investigations. We have over 30 institutional research board approved clinical trials undergoing right now. I'll talk about some of them today, and we do a lot of other sort of custom algorithm creation for things like deconvolution algorithms, a lot of age related algorithms, and including things like mitotic clocks and telomere estimators. And so our idea is that we want to be able to provide everyone, either patients or even direct to consumers, with information about their epigenome, which helps them make the right clinical decision at the right time. And so that's a little bit about us. Typically what we do commercially is offer these sort of direct to consumer testing. And this is right now 98% of all of the work we do is directly with medical providers, particularly medical providers in the cash pay sort of integrative space. And so we do a lot of this test where we'll collect blood. We prefer blood, as most of these algorithms are still only validated in blood. And then we're able to receive those results back to our lab and then report a lot of epigenetic analysis over the course of the next few weeks. We do a lot of different reports right now via this epigenetic methylation interrogation. We do also, though, have a lot of reports that are specialized in longevity. And so we do a lot of these biological age-related clocks. We have our sort of true age report, which is a comprehensive epidemiological review of all the things that we know influence biological age in a positive or negative way. We do things like intrinsic and extrinsic aging breakdowns, where we're actually able to quantify immune cell subsets. So, right now we have algorithms which are capable of diagnosing at least 12 different immune cell subsets. And we do telomere length as well, although not one of our favorite, I would say, markers of aging, definitely something that is still related and unique to those sort of hallmarks of aging. And so we definitely specialize in this. And one of the reports that I want to talk about the most, spend the most time on today, is sort of this pace of aging clock. I think that this is a very sort of underutilized clock, and it is incredibly accurate and incredibly predictive of disease. And so definitely want to spend about a little bit of time on that. However, TruDiagnostic just generally has a lot of aspirations outside of the field of aging as well. One of the things that we hope to do is to offer a lot more reporting and insights into both medical and industry related fields, as well as direct to consumer offerings. Some of the ways that we're going direct to consumer will include things like the exposome, looking at methylation to sort of say how much you might have smoked or drank across your lifetime, or how many toxic metals you might have been exposed to, or plastics, et cetera. Doing things like fitness and nutrition. We already even have a report right now that talks about if you're likely to lose weight with caloric restriction. And we plan to develop that into other areas as well, such as neurocognitive reporting. I think even some of the previous speakers on epigenetic methylation have talked about some of the behavioral things that we can actually see in epigenetic signatures. And we plan to go even into things as simple as aesthetics, with the sort of the first ever phenotypically trained methylation-based skin aging clock. And so we definitely plan to expand on this. And the way that we plan to do that is by gathering a lot of data. These new health insights and these new health algorithms require substantial amount of data and covariate data to then create these penalized regression models or neural net models to have ways to predict these outcomes. And so one of the ways we've been able to be very, very lucky to do this is, as I mentioned, the majority of our providers, I should say, majority of our kit sales are to clinical medicine providers. And as a result, these cash pay integrated medicine physicians are often tackling aging as a primary outcome, and their patients are highly motivated in this area. And so what we're able to do is to capitalize off of the things they're already spending money on. So for instance, blood testing, lab testing, telomere testing, skin glycosylation testing, and others, to sort of build out these covariate panels, which we hope will influence our algorithms to be even better as time goes on, and continues to help us build this massive database of information. One of the other things that we hold as sort of a core tenet of our philosophy is this the ability to look at this multi-omic picture. I think that if you reflect back on some of the shortcomings of sort of the genetic revolution, I think a lot of people expected it to answer a lot more questions than it actually did. And one of the reasons it was a little bit limited is because it's only one part of the picture. You know, all of these things from, you know, the sort of the basic dogma of biochemistry, from genomics to epigenomics to transcriptomics to proteomics and et cetera, all of these things are independent biomarkers, and we want to be able to look at all of them as a big picture. And so a lot of what we're doing is building these multi-omic data sets. And we're doing that by getting a lot of genetic information, not just 23andMe, but giving an example of obviously some of that genetic information, doing a lot of proteomic analysis and metabolomic analysis, lipidomic analysis, and many, many others. And what we hope to do is to be able to train methylation to predict some of these other fields as well, to get a more complete picture of health, all through what we hope is one day a very cost-effective solution to do one type of test with many, many different insights. And so that's sort of our philosophy, and we've tried to apply that to several different algorithm creations. One of the ones that I will talk about today is this Dunedin pace of aging metric that we've licensed from Duke. We've also licensed some mitotic clocks from the Van Andel Institute to look at things like stem cell depletion, as well as markers of senescence burden. We've done a variety of deconvolution methods to be able to predict the amount of cell subsets in each type of sample. We've done, as I mentioned obviously earlier, telomere length clocks. We're creating frailty predictors and phenotypically trained skin algorithms. And one of the things we're doing with that big multi-omic data set, we have over 10,000 patients with full proteomic data, full metabolomic data, and full genome sequencing, in addition to our epigenetic measurements. And we're hoping to use that in partnership with our Harvard and Partners Biobank to create one of the best death predictors and one of the best phenotypic age trained predictors as possible. And so we're really excited about that, and are even going into, I would say, even more specialized fields in the aging community, looking at those hallmarks with even some senescence immune deconvolution methods, so we can predict actually the burden of things like senescent T cells, all with one drop of blood. And so, so again, this is sort of our, I would say, our plans in the future, and we've already in the past year taken many steps to execute on that. And so going back to sort of what we're offering in relationship to aging, these are some of the reports. However, the one I really want to go into for the remainder of my time is the Dunedin pace of aging metric. And so before I go into that, I want to talk just a little bit about these history of clocks. And I know that there have obviously been several great speakers who have gone over this today. However, some of these initial clocks were sort of what they called the first generation clocks, were chronologic age clocks, which were trained this methylation data to predict the chronological age of a participant. However, you know, if not as clinically relevant as we would want it to be, because usually if you want to know the chronological age of someone in a healthcare setting, you can just ask. And so the second generation biological age clocks were trained against different things. You know, Bobby Brook from the Clock Foundation has talked about how the Grimm age was targeted to predict death, and you know, Pheno age was trained to predict markers of morbidity and mortality through some blood-based biomarkers. And so the first generation clocks were sort of these chronological clocks. The second generation clocks were sort of those trained against outcomes or health-related outcomes. But what I want to talk about today is what one particular study is deemed as the first ever third generation clock. And this is this Dunedin POAM, or pace of aging metric. This is work that has been done mainly by researchers at Duke and Columbia, and we've been lucky enough to work with them to hopefully help improve that and you know, change it from even blood to also saliva-related collection methods. And what this does is it's able to tell you at the exact same moment that you take it how fast your current pace of aging is. So this is separated from an overall biological age, and I think that this has some value, particularly for people who have lived, you know, previously unhealthy lives, but then want to start changing their life and implementing better recommendations and sort of seeing how they can impact their own rate of aging as the biggest risk factor for chronic disease and death. And so this is a really, really exciting algorithm because it captures something a little bit different. One of the other reasons it's pretty exciting is because it is by far one of the most accurate algorithms. Here you can see on this sort of slide what we call this ICC value, so the interclass correlation. And this is if you take two of the exact same sample and run it twice, how much of those results correlated to each other. And unfortunately, this has been a big problem in epigenetic methylation clocks. The amount of noise sometimes has, these clocks have large margins of error. So for instance, the 2013 Horvath clock had a mean average error of right around 2.9 years. And that can definitely limit the specificity and sensitivity of some of these investigations. And so this Dunedin pace of aging algorithm is also very, very accurate and precise, meaning that from one sample to another, if you have a large amount of change, you can be very, very certain that it is statistically significant. And this allows for personalized medicine investigations. You and I might each take the same medication, but then have different responses as it relates to our instantaneous rate of aging. And so this is an algorithm we like because it is captures an instantaneous parameter. It also is incredibly accurate. And then, as I'll talk about now, is also incredibly predictive of healthcare outcomes. And so this particular algorithm was created over the course of a longitudinal sort of cohort. It started in 1975 when over 1,000 patients in New Zealand at age 3 were enrolled into this cohort. And every year they track this cohort to measure age-related biomarkers. And so this cohort is very unique in the fact that it represents a longitudinal related cohort where we're tracking the same patients across their lifespan. So this obviously started in 1975, but it was additional investigations are being completed on these same individuals now that they're 45 years of age. And so some of these graphs, which I'll show you here, this is their performance on several phenotypic age measurements at age 45. So for instance, what you can see here is the one-leg balance testing, where if you look on the x-axis, you'll see that pace of aging, anywhere from 0 to 2 biological years per year. And then you can see their performance on their balance. And as you can see, this is highly correlated. The faster you age, the worse your balance is. And goes to show you that this is a great marker of phenotypic related events. The same actually holds out to grip strength as well on markers of sarcopenia and muscle mass. This also extends to even things in the brain. We're talking about things like cognitive decline. The faster that you age, the worse your performance on all of these quality of life metrics. And I think that is one of the things that is most exciting about this is that I think there's sometimes a false dichotomy between health span and lifespan. And this is actually able to capture both, where if you improve the rate of aging, you can then improve all of these markers of health span, but also increase longevity. And so this isn't just related to IQ as well. It's also related to things like MRI images of the brain, where the cortical volume is highly associated with rates of aging. And it's even applicable to facial aging. Actually, some of the most applicable is with facial aging. And so one of the reasons I always like to emphasize this as well is when we talk about epigenetic clocks, it can be a little bit esoteric whenever you're talking about relative percentages of risk. But this is actually a way that we like to demonstrate the impact of aging, not just on markers of health span or lifespan, but also on just aesthetics. If you look here, all of these individuals are the same age. They're all age 45. These are computer generated images of this entire cohort. And as you can see on the left, those are the slowest aging members of the cohort. So those are the 10 members that have the lowest rate of aging. Whereas we put on the right, the members that have the fastest rate of aging. And so what we see here is that these people look vastly different, almost 20 years apart. And in fact, because they might be, some have been aging at 1.9 to 2 biological years per year, while others have been aging at 0.5. And so this is something I always like to demonstrate, that you do age from the inside out, and that paying attention to your aging won't just improve all those health span related metrics, it'll also improve your aesthetics and even your lifespan. And so this algorithm is also really exciting for its use in picking up how clinical interventions are actually working. And so here is an example from the CALERIE trial. So this is a trial where over the course of 2 years, they did 25% caloric restriction. And as you can see, the Dunedin POEM, the pace of aging metric, is by far, I would say, the best at picking up the change in biological aging associated with caloric restriction. In addition to that, it also tends to pick up things like cognitive dysfunction or mild cognitive impairment and dementia better than most of the other age-related algorithms. And so we're very, very excited about this and already have some great data in a lot of interventional trials. As I mentioned, we have over 30 going on at the moment. Just to talk about some of them, which are probably most notable, we are about to submit for publication a study that looks at longitudinal effects of COVID-19 and the mRNA-based vaccines. And we found some very, very interesting things here. In particular, we saw that people who had COVID over the age of 50 had negative results as it related to most age-related metrics. And under 50, they actually had positive age-related results, meaning that we're sort of hypothesizing that, for people under 50 who have low burdens of exhausted T cells, they're able to mount a hormetic response, which improves their sort of aging rates, whereas those over 50 maybe are not able to. And we also found some very interesting things as it related to mRNA-based vaccines. And we also found that in particular, the Horvath DNA telomere length measurement was actually significantly diminished in most patients who had COVID-19, which backs up many of the other publications showing that telomere length is decreased with COVID-19 infection. One of the other areas that we're very excited about is sort of quantifying senescence and senescence burden. And so we did a trial on a popular senolytic, the dasatinib and quercetin. In 22 patients, we looked at them doing 50 milligrams of dasatinib and 500 milligrams of quercetin 3 days per month for over 6 months. We took methylation measurements at baseline at 3 months and 6 months in both blood and saliva. And we also performed activin A testing, beta-galactosidase testing, and the newly discovered Buck Institute biomarker of senescent cell apoptosis, sort of that prostaglandin-related biomarker. And we're really excited to submit this for publication in the next few weeks. And what we actually saw was that this had some different results. We saw a big difference between saliva and blood, but for most of the age-related biomarkers, we saw actual age reversal for the majority. And so that was exciting as well. And just to let you know, some of the other trials that we're investigating are things like fasting mimicking diets, things like the Prolon or Volter Longo related diets, looking at electromagnetic fields, doing everything from telomere supplementation to plasma apheresis to stem cell therapies. And again, the way that we're able to do this is through our partnerships with these clinical providers, where we're offering, the ability to do everything from IRB approval to different biomarker analysis to things such as metabolomics or proteomics. And so, we've got a lot of these studies going on, and we're really excited to now start adding objective related results to which interventions are going to reverse age the most with these methylation related diagnostics. And so I know that was a lot of information in a short amount of time, but would love to answer any questions which are available.
Great. Ryan, thanks very much. Is that all you've done in a year?
We've done all of that in a year, yeah.
Is that all?
That's it.
The question came in on the pace of aging. Does it measure negative aging rates?
So technically, a negative aging rate would be aging at a rate of less than 1 biological year per year. And so the answer is yes, it does. So for many of those cohorts, they're aging at a rate of 0.6 or 0.75 biological years per year, meaning that there's not a one-to-one comparison between these algorithms and the other epigenetic clocks. But the idea would be that I think that if you're aging at 0.75 years per year, over the course of 10 years, you would then be sort of anti-aging around 2.5 years biologically. And so I think that's sort of the philosophy that we adopt in most of these trials.
Brian, Dennis, I'm sorry to interrupt. I think Greg Fay's question had to do with, can you rejuvenate as opposed to slow down? So as you're measuring things, for each year that goes by, are you going back a year or 2 or 3? Or I think Daniel Ives was claiming that at least in his models, he was shaving 60 years in 17 days or something like that.
Yeah, so we're seeing multi-year age reversals with most algorithms that are measuring overall biological age. But the way that this particular rate of aging algorithm has been defined is not to show negative results. And so unfortunately, it would not show our age reversal, but we can show significant diminishing of that aging process.
I think that was Greg's question. Sorry, Dennis, go ahead.
Yeah, no, and I think Ryan, we're out of time, but I'd like to have heard kind of what your business model was and how you were going to figure out how to make money and things like that, and a little bit more about the team. I mean, that's an enormous amount of work you've accomplished in a year, and I also, you started and never went back to it. the choice to kind of go direct to consumer out of the box, and why you did that, and where that's all going. So there's a lot of ways you can go with this, and I'd be really interested to following up on some of that. But I think that for now we have to put a stop to it. So thanks for the presentation, and hopefully we can chat later.
Yeah, thank you all so much, and I appreciate you having me.